Welcome. Thanks so much for joining us today for Advanced SPARKvue Skills. Over the next hour, I hope to answer questions that you may have coming in like this. Can I record sensor data away from my computer? Or can I associate sensor measurements with other sources of data? Maybe something I measure with a meter stick, for example. How do I transform data in SPARKvue? There are a lot of measurements you can get from sensors or typing in data, but can you transform those in SPARKvue itself? Can I create startup files to reduce my students' lab setup time so they can jump directly into the data collection and analysis, the things we really want them to focus on? And can SPARKvue measure fast signals? So I hope to show you yes or how to for all of these questions today. And in doing so, I'll jump through a number of activities. The first activity we're going to do is monitoring room carbon dioxide levels here in our video studio. Then we'll jump over to doing an investigation of the pH of some household liquids. We'll take a look at the relationship, if there is one, between gas pressure and volume. Then we'll look at sound waves, and finally we'll wrap it up by looking back at that sensor that's logging carbon dioxide levels to see if it changed during the course of our webinar. We'll be stopping throughout with interludes to answer your questions as a group, but I'm grateful, as I said, to Heidi, who will be here answering those questions live in the Q&A. So send those questions as you have them. All right, so as you saw in the invitation to this webinar, there's some prerequisite knowledge. We presume you know the fundamentals of data collection and analysis with sensors, creating graphs, changing sample rates, saving and sharing files. If you don't, and you're watching the recording, you might pause now and take a look at the resources here, a quick tutorial video, or the predecessor webinar for this, Introduction to SPARKvue. Otherwise, if you are with us live, you got these links in the registration information, so you can always revisit those in the past. All right. So let's jump directly into room carbon dioxide levels. In this activity, I'd like to ask the question, first, what do you think is the current CO2 gas concentration here in this room? This is a fairly large room. It's our video studio, about the size of, and Heidi's pasted those links into the chat there. Thanks, Heidi, if you want to jump to those after the webinar. What do you think is the CO2 gas concentration in the room right now? It's just Heidi and me in this room. It's about a typical classroom size. If you have any thoughts on what this might be, don't worry if you're right, you're wrong. Please do share them in the chat, and we'll see if you have any predictions about what the current CO2 level would be. I've been in this room for a couple hours. Heidi just joined me a few minutes ago. But if you have any thoughts on what the CO2 level is, or what units are used to measure CO2, or anything like that, please share your thoughts in the chat. Over the next 45 or so minutes, Heidi and I will be here in this room. The door is closed. Do you expect the CO2 level to change over the course of this webinar? If so, how do you think it might change? Welcome your predictions there in the chat as well. And overall, how can we actually measure this? So as I wait for your responses there in the chat, predictions about what do you think the CO2 level is right now? How do you think it might change over the course of the webinar? I'm going to show you that we're going to use a wireless CO2 sensor to make this measurement. The wireless CO2 sensor can be used directly with SPARKvue, as I'm going to show in a moment, but we're going to use a special feature of this. So thanks, Sabina. Sabina predicts maybe 0.3%. Appreciate your prediction. And of course, we're going to use SPARKvue. Now, coming into this webinar, you're hopefully familiar with the basics of SPARKvue, and you may enter this experiment and say, you know what? I know how to get data using the sensor data path, so let me follow that, and we'll at least answer this question. What is the current CO2 level? Marie predicts 450 parts per million. Great, thank you both for your predictions there. So I'm going to turn on the power to my wireless CO2 sensor by tapping the power button. I see that the battery light blinks red briefly and the Bluetooth light is blinking red. Judy asks about moles for units. Yeah, if you want to revisit that, Judy, after we take a look at the calculations, you could transform measurements from one set of units to another set of units using the calculator. Neat question. So I'm going to go to sensor data kind of naively, and I'm going to connect it to my wireless CO2 sensor so we can at least initially answer this question, what's the current level? And then maybe realize why what we know about SPARKvue right now might not be the great best solution for doing this. So I'm going to connect directly to the CO2 sensor using the sensor data path, and I might choose something like digits and graph, at which point you may notice down here that in the live data bar, we can see that the current reading for CO2 concentration is 824 parts per million. That's ppm. So that's one way to measure those units. We could, of course, convert that into something like percent, but since it's a small number, parts per million is a nice way to look at it. And of course, if I hit start here, I can begin recording that CO2 level. And if I was able to leave my computer doing this for the next 45 minutes, this would be fine. We could see if it's changing. However, I need to use my computer to do the rest of these activities. So I'm actually going to stop now. You kind of realize, well, I can certainly get data quickly in SPARKvue, but the way that I normally record data live with a connection between the sensor and SPARKvue running on my computing device kind of monopolizes my computer, or at least SPARKvue on my computer, and I can't do anything else in SPARKvue. So I'm going to close SPARKvue and show you that there is a dedicated path from the welcome screen in SPARKvue that's dedicated to this feature we call remote logging, which is something that the wireless CO2 sensor supports. So let me return to SPARKvue and let's follow that remote logging path. And we're actually going to see this twice today. We can use the remote logging path to both initiate remote logging, that is data collection without using SPARKvue and streaming the data directly to SPARKvue, and we can use the same button to retrieve it. So let me go to remote logging. I'll make sure that my sensor is powered on. And this wireless devices screen in remote logging gives me a choice of sensors that are available for logging or sensors that already have data. Of course, the CO2 sensor does not yet have data on it. So I'm going to click the CO2 sensor here to connect to it via Bluetooth. It will make that Bluetooth wireless connection. And then it will give me some options for configuring how the remote data should be logged when this sensor gets disconnected from SPARKvue in just a moment. If I have a more complex sensor like a weather sensor, I can choose to turn certain measurements on or off, but the CO2 sensor is simple in the sense that it only has one measurement, CO2. So I'm going to just focus here on sample rate. Now, this is always an important consideration, as you might have seen in our first introduction to SPARKvue webinar for some experiments, but especially with remote logging, it's quite important that I log fast enough to capture any phenomena I might be interested in, but slow enough that I don't just fill the memory. And helpfully, as I change this sample rate, you may notice below that there is a prediction of how much memory the sensor has. So if I collected data at one sample every 2 seconds, it would fill up the memory in about 1 day and 8 hours. And as I slow the sample rate here, you can see that it's now giving me days of memory available. I think for this next 45 minutes or so, I'll sample once every minute. And at that rate, the memory wouldn't fill up for over 39 days. Now, there's an important caveat listed below. Actual duration may be limited by battery life. And for the power-hungry CO2 sensor, it certainly will be. And we'll talk about that when we retrieve the data. But for now, what I'd like to show you is that I've set up the sample rate. And right now, my sensor's Bluetooth LED is blinking green. It may be tough to see in the video here due to the refresh rate of Zoom, but it's blinking green. As soon as I press OK, I'm going to continue observing that blinking LED. And now I see that it is blinking yellow or amber. That means that this sensor is actively logging data into its built-in memory. So I'm going to set this aside. We'll return to this toward the end of our webinar and see as it's logging once a minute if there are any changes in CO2 level during the course of this webinar. Now, helpfully, SPARKvue says, hey, you've started data logging and here's a procedure for retrieving it. And basically, the process reverses itself. But one nice thing to know is I can close SPARKvue. I could retrieve this data on any device that uses SPARKvue. So there's nothing about coming back to the same computer that's required. So that sensor is now logging, and let us return to that later in our webinar. But now let's talk a little bit about when remote logging might be useful. In this example, I don't want to occupy my computer by streaming data live to it. So if you're doing longer term experiments, whether it's this coming hour or 24 hours or many days, remote logging is nice because the data is recorded directly into the memory on this wireless sensor. It's also nice if you're doing outdoor experiments. I am on a desktop computer right now. I can't lug it outside to maybe measure the CO2 level of the exhaust from a car. But I can initiate remote logging, and I can then take it outside and log the data. I could stop logging out there or bring it back in and keep logging and retrieve that data and see what happened when I was away from my computer. Now, this following thing doesn't require remote logging, but I want to remind you that SPARKvue is available on mobile devices, iPhones, Android phones. So if you need to stream data live and see what's the current CO2 reading, you could always take your mobile device outside. That's not so great for long-term experiments. I don't want to leave my phone outside, but if you merely want to go outside, keep in mind that you have two options, this remote logging process that we're doing now, or streaming data live to a mobile device with SPARKvue on it. All right, so we've initiated remote logging on the CO2 sensor. We'll come back to it at the end of our session and see what happened. Let's jump over to the next activity, which is pH of household chemicals. And for this one, we're going to ask some questions. How would you record and display the pHs of various household liquids? So let me bring into camera view here a tray where I have a number of things. I have a wireless pH sensor. That's the sensor we're going to use to make these measurements. I have some deionized water, which will allow me to rinse it. And then I have 3 household liquids, cola, ammonia, and cranberry juice. And I have a question up here. How would you record and display the pHs of these liquids? By that, I don't mean when would you put the sensor where. I actually mean in SPARKvue, what do you think a good display would be? How are you actually going to record this data? Fundamentally, we want to be able to identify a pH of cola, a pH of ammonia, and a pH of cranberry juice, the three liquids I have here. So if you have any thoughts, kind of logistically, in SPARKvue, knowing what you know now, how would you record and display these pHs? So I'll give you a moment to consider that, share your thoughts in chat. In the meantime, let me show you what we're going to do mechanically here with the sensor. The wireless pH sensor comes with a storage solution in this bottle. So to begin, before I can make a measurement, I'm going to twist off the storage bottle itself, set that aside so I don't knock it over. And just to keep the cap out of the solutions I'm going to measure, I'm going to push the cap upwards. So it's going to be out of the solution. Now, the storage solution here is something I don't want to contaminate my samples with. So I'm going to, before I make a measurement, rinse the electrode of the pH sensor, making sure I get up in the glass electrode right there where the measurement's actually made. And then I'm going to take a wipe and gently blot off even that distilled water that I used to rinse the probe. All right, so I am ready physically here to begin my measurements, but let me turn over to the chat and ask how we might actually go into this. So some of you know the secret answer. I'll skip that for now and we'll come back to it. Megan and Marie know that. Megan is Shannon. Yeah, so Jacob suggests in the table. That would be a great way to do it. I like that idea. Judy includes a table as well. Betsy says separate by runs. Fantastic. Thanks for sharing those ideas. Here are some ideas I often hear. Well, you know what? Why don't we just view a digits display of pH and write the values on paper in something like a table? That would work perfectly well. And none of these answers are wrong. I just want to show you some possibilities. Another person might say, well, we could graph the pH, record a single run, and during that run, switch the pH sensor between my solutions, and then just annotate with the graph annotation tool when I moved it from cola, when it was in ammonia, when it was in cranberry juice. So I'd have a single run of pH showing all those changes within a run. This is what Betsy has suggested, separate by runs. Why don't we graph the pH but record a run for each liquid? A run of cola, run number one, a run of ammonia, and so forth. And in SPARKvue, we can actually rename those runs. So we could have a run called cola, a run called ammonia, and so forth. So all of those are perfectly reasonable solutions. I think what I'm going to do, though, is show you a different process. Some of you know this already, but in Spirit, we're essentially going to be writing the values in a table, but that table is going to have the advantage of not being on paper, but being in SPARKvue itself. So to do that, we're going to learn a couple new things about SPARKvue. Well, new to some of you. So let me jump over to SPARKvue. And this time around, we're going to take control over everything. We are going to build our own experiment to answer this question: what are the pHs of these substances? Thank you all for your suggestions in the chat. So I'm going to go to this button called Build New Experiment. When I do, I'm basically in control of the layout of the first page of my SPARKlab. This works kind of like PowerPoint in that you can choose different layouts for the page. And then later you can say, well, in this section of the layout, I want a graph. In this section, I want a picture, things like that. So for this first time around, I'm going to choose this layout here that has a small item in the left third of the page and a large item in the right third of the page. I'll go ahead and select that template. And basically, the first page of my SPARKlab is built, page number 1, with those two placeholders in the places that are requested. Well, Saeed says a table would be useful there in chat. I agree. So for the left portion, I can use this selector and choose a table display. By default, it will give me a 2-column table, which I think is handy for this. Now, I'm going to ask, what do you think should be in the columns of this table? Do you have a preference for what's in each column? If you have any thoughts, please share them in the chat there. In the meantime, I'm going to turn on my pH sensor. And I think one thing that's obvious is I'm going to have pH in one of those columns, right? So if I go to select measurement, I might choose the right column. And you'll notice that there's no pH sensor. Well, that's because I haven't connected it yet. So when you start within a file, including those you're building yourself, we need to connect the sensor. So I'm going to go up to the Bluetooth button in the top bar. And with my pH sensor powered on, it should show up here as an available sensor. I'll connect to it. And while I'm doing that, Shannon suggests left column is the substance, right column is the pH. Great. And I think Sabina corroborates that, substance and pH. Great. So I've connected my pH sensor. And now that the sensor is connected, I can return and take your advice. And for the right column, choose pH. Now for the left column, I want to choose substance, which both of you suggested there. Now here's a nice little shortcut. Instead of going through and defining everything, I'm actually going to take this shortcut of just double-clicking the first cell. And my first solution here is cola. I'm going to type cola and hit enter. And SPARKvue is smart enough to say, well, you're in a table and you've typed something yourself. That's going to be a column of things that you, the user, are entering called user data. It defaults to a generic name, user data with no units, but that pencil next to the header for this column allows me to go in and say that this is the substance. And there are no units for this, so I'm going to delete it for this categorical data. So I now have a column for my substances. I could type these substances in later, but since Heidi is busy with chat there, I'm simply going to type them ahead of time, knowing that I could modify them later if I wanted to, but I'm going to pre-fill those just for convenience. All right, so I've made some progress here. I have a column of substances. I have a column of pHs. Now, I might just cavalierly say, I think I'm ready. Obviously, I'm going to ask a question a little bit later here on the right. What display do you think would be appropriate for this? You might think about that and share your thoughts in chat. But if I just naively went forward and said, oh, I think I'm ready to record, I'm going to press the start button. And look at that. I'll press stop quickly. Notice that the column of pH filled up quickly with the current pH reading before I even had the chance to put the probe in my first substance, cola. I will put it in there just to begin equilibrating to that. But the problem here is the following. When I created this file, new files by default start in periodic sampling mode. Periodic sampling mode means that there is a default sample rate for the sensor, in this case 5 Hertz. And that defines that when you press start, in periodic mode, the pH sensor's measurements are going to be recorded 5 times a second into SPARKvue. That's not what I want here because I need the time to be able to rinse the sensor between solutions, to move it from solution to solution, let it equilibrate. So let me essentially undo that. There's no undo button, but if I go to the experiment tools menu down here, the wrench and screwdriver, I can choose manage runs, delete last run, and it keeps my user entered data, but gets rid of that run of pH. So the solution here is going to be, it's going to happen automatically. If I look at the displays that I could put on the right side, I want a display that would allow me to see the pHs of various substances. You're probably familiar with line graphs. Line graphs are great for number versus number, like pH versus time, an interaction, or force versus time, or we'll see later, something, even user entered data that's numerical. But in this case, I have categorical data, cola, ammonia, and juice. In that case, something like a bar graph represented by this icon would be great. And when I pressed bar graph, SPARKvue was smart enough to know that, well, bar graphs go well, not with periodic sampling mode, but with manual sampling mode. So it automatically switched over to a mode of sampling that's appropriate for collecting categorical data, which is appropriate for something like the bar graph. So I'm going to define my y-axis of the bar graph to be pH, and the x-axis, I don't see substance here, but if you look at the top, there's a tab, a sensors tab, and a user entered data tab. And if I go to user entered, I can see substance there. So I now have a bar graph of pH versus substance. I'm going to turn that setting off here just to keep things clean. And now in manual mode, I'm going to press start. And in this case, pressing start does not record any data. When you're in periodic mode, pressing start records data at the sample rate. But when you're in manual mode, as indicated here, pressing start merely begins monitoring sensor data. I can see a live reading of the current pH here as a color of the run, 2.94 for cola in the first solution, and I can see it live in the bar graph as well. So this is not yet recorded data. I could take my time, make sure it stabilizes, and when it does, I need a way to tell SPARKvue to record that as a piece of data. There are 2 ways to do this. There's a check mark here called the keep button that's also duplicated down here. Either of these green check marks, when you press it, will record that particular pH at that moment into that row that you've clicked on. So I'm going to rinse off my pH electrode and blot it dry, knowing that in black there, I've just recorded the pH for cola as 2.92. I'm going to put the tip of the electrode for the pH sensor into ammonia. I can see the bar graph shoot up. And again, this is a live reading. It's not yet recorded until I press keep. So that looks pretty stable. I'll press keep. It turns to the color black, meaning that it is recorded. Once more, I'll rinse the electrode, blot it dry, and put it in my final substance cranberry juice, where we can see the pH plunge even lower. I'll give that a moment to stabilize. And when it does, I'll go ahead and press keep, either this check mark or this check mark. They do the same thing. And the following, I think I'm done. I have my 3 substances pHs recorded. I know they're recorded in black. This tends to confuse students who are new to manual sampling. And that is, why do we have a new bar? Why do we have a new measurement? The thing to tell them is, notice that this is not in black yet. I haven't recorded a pH for this line 4. And as long as I'm happy with the pHs above, and I am, as soon as I press stop, that's going to go away. It was never recorded because I never pressed the check button. So let's take a look at this bar graph, a very nice way to display the substance pHs. The bar graph has a lot of features that are like the line graph. You can rescale in either axis. And it has some things unique to the bar graph. I can turn on the numbers, so I can here see 2.92 for cola, 11.75 for ammonia, 2.46 for the pH of juice. And I can even do things like statistics and turn on lines that represent the maximum and minimum pHs that I measured. It's not so useful for 3 things, but you can imagine that'd be nice for larger sets of data. So I only measured 3 pHs, but I could have continued this process. And all the data I collected between pressing start and stop was recorded if I pressed keep, and it wasn't recorded if I didn't press keep. So let me jump back here and say a couple things. The sampling mode switched from periodic to manual automatically when I made the bar graph, but we always have control of that by going into the sample rate settings, and we can switch it over to manual, which I'll do in the next activity. And here's a quick animation of the differences between periodic and manual sampling. Files start periodic, new files, but they can be switched over to manual sampling by you, the user, or by actions like creating a bar graph. In periodic sampling, you press start, and at the sample rate for the sensor, data is recorded, and that recording continues over time at a regular periodic rate until you press the stop button, and all the data between pressing start and stop is a run. Well, if you're in manual sampling mode, by contrast, when you press start, readings are coming in, but they're not recorded until the user presses keep, saying, I want that data point. And then they can adjust things, and when they're ready for the next data point to be recorded, they press keep, and they can do this at an irregular rate if it takes more time to jump between samples. But similarly, after they've kept all the values, when they press stop, all of the data that was kept is a run of data. So each of these represents a run. Left side represents periodic sample, right side manual. All right. So here are some thoughts on popular ways to use manual sampling. These are investigations, and you notice that we have blue text and orange text. In each case, I've identified what you're measuring with the sensor in blue and what the user is entering in orange. Take a moment to look at those and see if you can identify any trends there. And as I do, I'll ask Heidi, are there any questions we should address as a group while they take a look at these?
No, there have not been any questions.
All right.
Able to answer some of the inquiries.
Great. Thanks for keeping those questions coming, and Heidi, thanks for answering those. So if you look carefully, let's look at the second bullet here. On the left side, I have temperature versus location on arm. So that might be something where I take the temperature sensor and I manually sample the temperature at the crook of my elbow. That's crook of elbow is a certain temperature. And then I go halfway down my forearm, that's another temperature. And then my wrist and my palm and my fingertip and so forth. You'll notice in the left side here, all of these user-entered data are categorical data, like the name of a location on my arm, just like we did with pH of household substances. On the right side, here's another experiment, temperature versus distance along arm. I could define, say, my shoulder as distance 0, and then if I noticed a trend with the categorical data, I could say, you know what, what's the temperature 5 centimeters down my arm, 10, 20, and so forth. And in that case, I would have numerical data for the user-entered data. So in this next activity, we're going to take a look at a numerical user-entered data activity. It is indeed the last one here, gas pressure versus volume. All right, so Heidi, thanks for answering those questions coming in. Let us jump over to gas pressure and volume. And in this investigation, I'd like to ask the question, how can we determine the mathematical relationship between gas pressure and volume? And in this case, gas pressure is going to be the sensor data measured by this wireless pressure sensor. And the user-entered data is going to be a number. It's going to be the volume as read from this syringe. The markings on the syringe are easily read. By the way, this syringe comes with the sensor, which is handy. So this experiment is just a nice out-of-the-box experiment. So with 30 milliliters of air at STP, I'm going to stopper that up. So I have trapped a certain amount of air in that syringe. And how can we determine this relationship? Well, as scientists do, let's collect some data and see if we can suss out a relationship between those. Now, at the end of this activity, we're going to extend it and try to answer this question. You're going to see a lot of setup involved with this, but we're going to ask, can we make it easier for our students to quickly discover this relationship for themselves in the limited lab time that you have? So let us, actually, something important here. This isn't an advanced SPARKvue feature, but it's something that's new and I think it's worth covering. So far today, I've been using the SPARKvue application. I have it installed on my Windows computer. Here it is. I've been using it for the previous two activities. This SPARKvue application, as you may know, is available as a licensed piece of software for Windows and Mac OS. It's available free in the app stores for Chrome OS, iPads, iPhones, Android tablets and phones, and it's also built into Pasco data loggers. Something exciting that's happened in the past couple months, though, is that we've released something called SPARKvue Progressive Web App. That's a mouthful, so it's often abbreviated PWA. It's probably easiest to think of as SPARKvue in a browser. So if you have a Windows, Mac, or Chrome OS device, and you have the Chrome or Edge browser, you can run SPARKvue for free in your browser going to the address sparkvue.pasco.com. And I'm going to do that right now for the next activity. And bottom line is there's only one thing that's really different about it in the activity we're about to do. And I'll show you, it's the way we connect sensors because we're in a browser instead of in an app. But other than that, you can essentially do everything crucial in SPARKvue PWA that you can do in the SPARKvue application, and it's a free app. If you want to learn more about this, we have some videos on different flavors of the PWA, things to know at this web address, bit.ly/pwa-vids, and I think Heidi will be posting them in the chat shortly for those of you who are live. So let me bring over a browser. I've closed the SPARKvue application, and I'm going to go to that address, sparkvue.pasco.com, and it's basically going to temporarily install SPARKvue inside my browser. Now, you'll notice this looks quite similar, and it functions, with one important exception, quite similar to SPARKvue. So in this investigation of gas pressure versus volume, I'm going to take this same build new experiment path. And this time I'm going to choose this template here, a large thing on the left and two small things on the right. And I'm going to make let me start over there. Start new experiment. I'm going to actually choose that same template we did before, a small thing on the left for my table and a large thing on the right. So if we're interested in two things, gas pressure and volume, and again, remember I'm in the browser here, but it looks like SPARKvue. If I want to measure the pressure and the volume of gas, I'm going to want two columns in my table. Now, if I go to select measurement, of course, my sensor is not yet connected. And here's where you need to know a difference between SPARKvue PWA and the SPARKvue application. Because this is in a browser, we have to obey all the rules of the browser about connecting hardware. The process is somewhat analogous, though. If I go to the Bluetooth button, as I would have in SPARKvue, in the SPARKvue application, I could now connect. In this application, I now need to launch this Bluetooth button to access the browser's own Bluetooth connection panel. Now, I prefer SPARKvues because this is a little confusing. You'll notice it says pressure paired. We don't have control over this. This is Chrome saying this is how I pair things. But at the very least, I can look at my pressure sensor and identify it here, 939345. I can click on it. It says paired because I paired it in the past. It doesn't actually mean it's paired, so it's a little confusing. But if I click the pair button, as long as I can get it to show up in SPARKvue's wireless devices screen here, I'm good to go and proceed the same way I would in SPARKvue. There it is. So that looks good. I just want to mention, by the way, even if you choose the sensor data path, you're going to have to press the Bluetooth button for using Bluetooth sensors in the SPARKvue PWA and the USB button to connect USB-based Pasco sensors, just because we're all fundamentally connecting to the browser here. So that is the difference between SPARKvue and SPARKvue PWA. I'll proceed now to choose the pressure for my right column. As I did before, I'm simply going to start typing. In this case, I'm going to measure volumes from 60 milliliters down to about 15 in increments of 5 milliliters. 35, 30, 25, 20. 15 is about as much as I can do single-handedly. And what would be an appropriate display? Well, I'm back to having number data and number data. as you think about an appropriate display, let me redefine this. User entered data. This is the volumes as I'm reading off of the syringe in milliliters. All right, so number versus number data, I think a line graph would be appropriate. So let me define the y-axis as pressure, the x-axis, again, is user entered data volume. And I'm almost ready to go, but for one thing, and that is, if I notice down here, this default sample rate is 20 hertz, the default sample mode is periodic. So I need to come in here and select manual sampling mode, otherwise I'd get 20 pressure measurements per second. Press OK, and now I think I'm good to go. I'm in manual mode. I'll press start, and because I'm in manual mode, I can take my time putting the syringe at the first measurement volume here, 60 milliliters. Press keep, and I'm going to go down the line fairly quickly here, keeping the pressure reading from the sensor for each of the corresponding volumes. So it's getting easier here as I get towards 30. Here's 40. I'm going to intentionally make a mistake here. And if I notice that mistake, if I haven't pressed stop, I can always go back. I forgot to go to the right place for 35. So let me click back in that cell in the table. And as long as I haven't pressed stop, I can correct that. So we're down to 30. I don't need to push or pull here. And now I need to push to compress it to 25, 20, and finally 15. All right, that looks pretty good. I think I'm happy with that, so I'll press stop. I've recorded that run of data with the manual sample data points. I can scale to fit that. And we see there's some sort of relationship. Now, I'm going to extend this. We could talk about that relationship right now, but I want to begin to think about how we could do this with students. How could we guide them through this experiment? And I'm going to propose that we kind of tweak this file to make it easier for them. So I'm going to rename the current page number 1 as record, and I'm going to build a second page by hitting the new page button. And on the second page, I'm going to choose this layout here with a large thing on the left and 2 smaller items on the right. And I'm basically on the left going to replicate my line graph of pressure versus volume. All right. And at this point, some of you may prefer to not have those lines connecting the data points. If we go to the settings for the graph, we can turn off the show connected lines, and that will be remembered in this file. So this is kind of nice when you're fitting data so that the default straight lines between points don't confuse students with the curve fit lines. Now, fundamentally, I want to ask students with their data, and I'll do with my data, so is there a mathematical relationship between pressure and volume as graphed here? And the way that we often develop this is we can create a model, a mathematical model, and see if that model fits the data that we've actually collected. Now, I'm going to choose a few fits and see if they work. I might start with a linear fit, and that looks pretty good. But if I go in here and try other fits like inverse square, well, that looks better. Is there something I can do besides just say it looks better? Well, these values in here, mean squared error and root mean squared error, if you remember the error in there, the smaller those numbers are, the better the fit is. So if I go in and try one more fit, maybe inverse fit, I can see that both looks good and has a much smaller mean squared error or root mean squared error than the other 2 fits. So I think that's probably the way to go. But how can I get my students to investigate that? So I'm going to propose in this empty space we have in the upper right, I'm going to go in and add what's called an assessment. Most of these are displays of data, digits display, table, meter, but there's something called assessment here. I'm going to add a multiple choice assessment, which is basically a suggestion to the students. Which of the following relationships best fits your P versus V data? And I'll give them some options. You might have noticed there's a long list of fits there. I'm going to try to constrain it to linear, inverse, and inverse square. I'll hit save. And I now basically have a prompt built into SPARKvue here that asks them, basically suggesting, hey, try these 3. I'm going to go and check the spelling. That looks good, so I'll lock that. And now this is built into this SPARKvue file. For this lower right corner, I could have something like a text box, and these could be further instructions or student notes. Many options there. But you can kind of see how I can add elements to my SPARKvue page that allow them to kind of be guided into the analysis. In this case, I'm going to rename this current page as Analyze, since the first was Record. All right, check that things work. Definitely the inverse fit was the best for my data. All right, so it looks like everything's working there. It looks like I've discovered this inverse relationship between the pressure, which is Y, and the volume. So instead of starting by saying, let's confirm Boyle's law, we've collected some data and we've essentially derived a relationship between these two variables for ourselves. I might call it Glenn's law. Let me save this data. What's kind of neat about the PWA is even though I'm in a browser, when I go to the main menu and choose save, it's just like I'm in SPARKvue. It gives me my, in this case, Windows operating system save dialog. And I'm going to save this file to the desktop. I'm going to call it gas pressure versus volume with data and analysis, just to keep things straight. So I've saved that file. By the way, if I save a file with PWA, I can open it with the SPARKvue app and vice versa. It's all the same file format. So the real question here is, now that I've set up some things for my students, could I give them a file that allows them to quickly connect to sensor, collect the data, and learn the relationship for themselves? So the answer, of course, is yes. What I'm going to do is I propose we turn off everything that I don't want them to see. I'll turn off the fits. I'll unselect the answer. I'll go back here. And if I go back to this experiment tools menu, I can choose manage runs, delete all runs. And if you think about it, this file is now set up so that if I save it and distribute it to my students, they can simply open the file, connect the sensor. It's already in manual mode. The volume's already set. They can always change it if they want. But all these suggestions, the displays I want, are all set for my students. So let me go back. And this time I'm going to go to the main menu and choose Save As. And I'm going to save it as something like gas pressure versus volume, and you might call it template or config file or something that would remind you that this is the version to give to your students as a template for collecting this data. All right, so that is all ready for them, and you can see that if you work through an experiment yourself and it involves some setup like changing sampling modes, creating displays, assessments, if you save that file without the data and assessments performed, it could be something that your students can start up with and save some lab time so they're getting to data collection and analysis even quicker. So I'm going to close the browser window here in SPARKvue since I've saved it. And just to continue our discussion here and prove that these files are compatible across PWA and SPARKvue, here's that file I saved a little bit earlier with data and analysis. I'm going to reopen that, and we as instructors are going to take it a little bit further. I see that I have an inverse relationship here, and for some instructors, it's fine to demonstrate that through an inverse fit. Other pedagogical approaches say, I want to make everything linear. I want a straight line, so the students are always fitting a straight line. In that case, they need to be taught that you could transform one of these axes in a certain way to make this a linear relationship. And if it looks inverse like this, one way I can do that would be to calculate the inverse of either the pressures or the volumes and graph that. So I'm going to show you how to do that using a powerful feature in SPARKvue called the calculator. One general way to get to the calculator is go back to Experiment Tools, and you'll see there's an option for Calculated Data. This brings up our calculator, and the calculator works kind of like a programming assignment statement. I'm going to create something on the left side and give it a name. So INV-VOL for inverse volume is simply the name I'm going to call this transformation of data. So it's going to be a new set of data called INV-VOL for inverse volume. Then I put an equal sign, and on the right side of the equal sign, I define a mathematical transformation. So what do I want to do to get inverse volume? Well, going down here to the calculator, I want to do 1 divided by, and here's the tricky part. How do I get all the volumes in there? Not just one value, but every volume measurement that was entered as data. Well, there's a big orange measurements button. And if I go in here, you can see I can put any sort of measurement in here, whether it's sensor data or user entered data. So I'll choose volume. And if I want, I can define the units, which are going to be inverse milliliters, given how I entered those volumes. I'll hit done here and press OK, and nothing happens. But behind the scenes, I've defined basically a new measurement called INV-VOL for inverse volume. And the powerful thing about the calculator is you can put calculated measurements anywhere. You can put measurements directly from sensors or directly from users. So if I want to transform the x-axis from volume to inverse volume, I'll go under user entered, and I can see that calculation is here. And if I scale the fit, you'll see that I have linearized that data by doing a transformation from volumes to inverse volumes. There's another way to get to the calculator. If, for example, I went into the table and added another column, If I know I want the calculation in this column, I can simply press the Select Measurement button. And under User Entered Data, there's an option to create or edit a calculation. So I'm going to create a new one. And for this calculation, maybe I could show students that, well, if it's inverse relationship between pressure and volume, then the product of those two should be fairly constant. So PV equals, so the outcome of this calculation will be called PV. And I'm going to multiply all my pressures, or each pressure rather, by each volume. And that's going to be kPa ml. Press OK. And because I started with the Select Measurement button, it knows to fill in that calculation here. And I can see that there's not a lot of variation here, of further evidence that there's an inverse relationship between pressure and volume. All right, so that takes a little bit further introducing the SPARKvue calculator. We've looked at the build path here a couple times, both to build our displays for pH of household substances and for this gas pressure versus volume. Heidi, any questions we should address before moving on to sound waves?
No, again, we've been having a lot of good questions coming in Q&A, and
fantastic.
we've been able to answer them.
Cool. Thank you very much. Thanks for the questions as well. All right, so before we return to our logging CO2 sensor, I have one more quick activity, and it's quick in a couple of ways. The question we're going to ask and answer here is the following. I have a wireless sound sensor, and I have some chimes that can produce some tones. And the question is, how can we view the sound waveforms? Technically, the sound pressure level changes when I hit those chimes using the wireless sound sensor. And then we're going to see if we can do something else and determine the sound's frequency. These chimes have different frequencies. So to do that, we're going to jump over to SPARKvue again. I'm going to close SPARKvue just to disconnect any sensors and relaunch it. Hopefully you found the PWA helpful. Again, the key there is just a different way to connect sensors. I'm back to the application though. So if I naively just said, well, wireless sound sensor is a sensor, let me choose the sensor data path, turn on my wireless sound sensor, connect to it via Bluetooth. And once this sound sensor connects, we're going to see that it offers a number of measurements, either sound waveform or sound level. I'm interested in waveform, so I'm going to keep the wave measurement on and maybe choose graph. And right away, notice that the default sample rate for the sensor is quite high. Sound waves specifically have to be measured at fairly high sample rates. So it defaults to a kilohertz, much faster than any other sensor that we've looked at. So let me just press start and hit a chime. I'm not going to talk after I hit the chime so that my voice isn't picked up, but let's see what happens. And stop. Well, that's 3 seconds of data, so that's 3,000 data points. If I zoom in here along the x-axis, well, something's happening here, but I'm getting some sort of beats. And if I look at individual, well, are these individual waveforms? I don't know, but at the very least, they're really jagged. I might want some more data. So if I come over to the sample rate, I can bump that up to a maximum of 2 kilohertz. Does that make a difference? I still get the beats, still is jagged. So there's something here, I'm running into a barrier where I think I need to sample even faster than the graph allows me in periodic mode. So that is true. We're maxed out at 2 kilohertz here because that's about as fast as we can actually record every single data point coming from the sensor. But there is a solution to this. So let me start a new experiment. And I'm once again going to choose the build new experiment path. This time around, I'm going to choose a full screen display. And because I have a sound sensor connected, and this only works for sensors that can sample really fast, like sound and voltage and current, I have a display you might not have seen before, and it is a scope display. I'll choose the scope display, and at first pass, it looks a lot like a graph. So I have sound wave on the X, I have time on the, I have sound wave on the Y, time on the X, but notice the time here is fractions of a second, 0.003 seconds. And notice that the sample mode has automatically been changed to something I can't select otherwise, other than creating a scope, which is scope mode. And look at that sample rate, 20 kilohertz. So 20,000 samples every second. Well, how does it possibly do that? Let me hit start and hit the chime. And the way it does that is it's not accumulating all the data. It's not actually recording any of this data. It is simply streaming data at the requested sample rate, really fast, 20 kilohertz here, and it's showing it in a frame of data to fill the available view. So I'm going to try to get a nice view here. And I'm going to do a couple of things. I'm going to look at the tools, some of which look like a graph, but I'm going to turn on this positive trigger. And that means that this trace is always going to start on an upward zero passing moment. So it's no longer jumping left and right as much when I hit the chime. And it still looks a little jagged. So I'm going to press this plus button. And as I press this to add data points, notice that the sample rate is adjusting automatically. The frame rate's slowing down because each frame has more data, but I'm getting a smoother curve now. And the question would be, well, if this is only monitoring data, how can I actually capture a representative waveform? And the answer is you can press stop when you like what you see. So I'm going to hit the chime. When I like what I see, I'll press stop. All right. So as soon as I press stop, this basically becomes a run. It's just this snapshot of sound pressure level or effective sound pressure level versus time. And now I can do things that I can do on the graph, like turn on a coordinates tool. And I can put this at one peak, use the delta tool to figure out the period between peaks, and from that I could find the frequency and so forth. Let me turn that off for a second. I could compare waveforms. So let me hit the shorter chime now by hitting start. And I can show both of those. So purple is the longer physical chime, green is the shorter physical chime, and I can begin to figure out what are the differences between these two chimes. Now I started on the path of trying to figure out what the frequency of the green rather was. It turns out there's a dedicated tool, a dedicated display in SPARKvue. If you're always asking what's the frequency of the signal, there is a display. So I'll build a new page, create a full page display, and this is the other special display you get with fast sampling sensors. It's called the FFT. FFT stands for Fast Fourier Transform. And as soon as I put on the Fast Fourier Transform, notice that the x-axis is fixed at frequency. So I'm going to make the y-axis be my sound wave. And what this is basically doing is it's performing a calculation and displaying it in the FFT. And this is a spectral analysis. So it tells me at each of these frequencies, what's the strength of the signal. And you can see that for the two chimes I had recorded for runs 1 and 2, I have a peak. And these peaks correspond, if I click directly here to turn on the coordinates tool, they correspond to the frequency of that signal. So this can be done live as well. If I hit start, I see a peak at the peak of that frequency. And instead of having to go back to this graph, this scope and calculate it, this FFT display is doing that calculation live. And it gets really nice when you have complex waveforms. I'll hit all three chimes. Whereas on the scope, this would be a messy purple line here going up and down. On the FFT, I can see immediately that I hit three chimes and I have three core signals here representing the frequency of each of these three chimes. So the FFT, or Fast Fourier Transform display, is great if you want to look at the frequency components of signals. Now it's often for things like voltages from a circuit or sound waveforms, but this can also be used in mechanical systems. You have a shake tower, you're pushing it, you can see how that shake tower responds, what frequencies it's vibrating at for the natural resonance. All right. So I'd be remiss if I didn't mention that I've been showing you how to build these things from scratch, showing you how to build your own scope display, FFT, build your own displays. But we acknowledge that for some experiments, like the ones I've shown here, it's often nice to just have something student ready. I wanted to show you how to do it from scratch because now you can build anything you want. But as an example, if I go back to SPARKvue and start new experiment, and I choose the sensor data path, if I have a sound sensor connected, as I do now, notice there's a section called Quick Start Experiments, and it does give me the option to jump directly to a scope or directly to an FFT. You know how to build those yourselves if you want, but I can jump there directly. Similarly, if I connected a pH sensor, there's a pH of household substances available in the Quick Starts, and there's a Boyle's Law experiment if I connect a wireless pressure sensor. So those are some shortcuts, but now you know how those are built, and you can build your own variations no matter what sensor you're using. All right, well, we have 7 minutes left. Heidi, any questions about the scope and FFT before we retrieve our carbon dioxide level data?
Okay, so there is one from Boris. Can you see real and imagery components of FFT separately?
Oh, so real and imaginary. No, it's just going to do the trace that you saw there. That's an interesting thing. I haven't personally seen FFTs that decompose it into real and imaginary, like for LRC signals. I have to think about that. But the FFT is just going to do the analysis as you saw there using the standard fast Fourier transform algorithm. If you need more details about that, feel free to email me, Boris, and I can talk to our programmers and get you any additional information about that algorithm. But I believe it's just the standard FFT algorithm. Interesting question. Thanks for that. All right. So we have our CO2 sensor that's been logging over the course of this webinar. How do I know it's still logging? Well, if I bring it here, it might be tough to see again, but the Bluetooth light is still blinking yellow. All right, that means it is currently logging data and has been doing so since I set it out. Now, I've closed SPARKvue, I've done different things. As I mentioned earlier, I could retrieve this data on any device that has SPARKvue. It doesn't have to be the same device, same platform. I do need SPARKvue to retrieve it, but or other Pasco software like Capstone. It even goes cross-platform like that, but I'm going to retrieve it in a new SPARKvue file. And to retrieve it, as I mentioned earlier, we'll return to remote logging. And you might naively sit here and say, why isn't it showing up? All right. Well, my CO2 sensor is not showing up because when I entered remote logging mode half an hour or so ago, it wanted to preserve all the power on this to recording data and saving that data to its memory. So it turned off its Bluetooth radio to save power. I need to turn that Bluetooth radio back on. How do I know it's not on right now? Well, it's only blinking yellow, and that in the LED language for the sensors means it's only logging. If I come and press the power button, as indicated right here as a reminder, briefly press the power button to awaken the sensor. I'll press the power button for a moment, and I go, no, it's hard to see over Zoom, but if you'll trust me, the LED is now blinking two colors. Yellow, meaning it's still logging, and red. Red meaning the Bluetooth radio is now on. And at that point, it shows up as a sensor available to connect that has data. So I'll click to connect to that sensor, and there's an important dialog that comes up when you connect sensors that have data logged to their memory. And that is, what would you like to do with it? There are three options. One is simply don't connect, it continues logging. You can simply delete the data, or you can download the data, which is what I want to do in this case. However, I don't want to leave the data on here for someone else because they'll get this dialog and have to figure out, is this data important? So before I press download data, I'm going to check this box, delete data from sensor after download. I'll press download data, and much like the sensor data path, it gives me the option to choose a display or displays from the templates. I'll choose a graph display, and there we go. So over the course of 2,700 seconds since I started logging, it logged the CO2 level in the room once every minute, as I specified in the sample rate. And we can see it trending up here as I was blabbing on, and alongside Heidi here. So we had some humans in the room, and even in this large room, it seems like we can see an upward trend. I might even do a fit line to this, and I can see the rate at which it was increasing. One really nice thing to know about remote data logging, though, is I can't think very well in thousands of seconds. So if I go to the time axis, I could switch this to something like minutes. So I did measure, wow, right on 45 minutes. That was fortunate. But even better than that, if I come under time and instead of time, I choose date and time, it now tells me the actual calendar time and clock time. So I can see at which time I started, and the, for example, coordinates tool updates to show I started at this date at this time and that reading. So when you are doing log data or any long-term experiments, it's really handy to be able to switch from time mode to date and time mode. So we can see the CO2 increase, and tools like the linear fit are also going to begin showing us data in the units of parts per million over this clock time. All right, I do want to show you one thing. Let me open a file that I logged CO2 for a week, or actually 8 days, in the office here. I'll leave that up as we ask if you have any questions about remote logging. So this is now switched to date and time, and I started on a Wednesday in 2022, and you can see a Thursday, Friday, Saturday, Sunday, Monday, Tuesday, Wednesday, Thursday. So just over 7 days of CO2 data logged here. Now I had to supply power to the sensor. I'll talk about it in a moment. This sensor won't last this way on its battery. I'll talk about that in a second. But you might look for some trends in this CO2 level. This is in the office, not just in this room. So this is in my cube with other workers around me. And you might look for some trends about when we're here, when we're not here, when we go for lunch, when the custodial staff comes in. And I think all of those have little trends in here that you can answer by turning on coordinates tools and seeing what time of day do I get the dip there. So hopefully you can see some of that power of remote logging. Remote logging is available on most wireless sensors. You can go to the product page for a particular wireless sensor and you will see it says logging and gives you some specs. So we saw that I could have collected many weeks worth of data in terms of the memory of the sensor, but the CO2 sensor consumes a lot of power. So if you're just running it off the battery logging, I would get about 18 hours of data collection. This contrasts with something like the temperature sensor, which is not power hungry, and with a fresh battery there, I'd get about 35 days of logging. If your battery ever runs out during remote logging, don't worry, it elegantly saves the data before shutting down, and you can then charge it and retrieve the data afterwards. So hopefully you'll consider remote logging. Not every sensor works in remote logging mode, where it saves the data to its built-in memory, but most of the wireless sensors do. There are a few exceptions like SmartCart, PhotoGate, motion sensor don't, but the things you'd expect like weather, CO2, temperature, pH, for environmental measurements all support remote logging, and even physicsy sensors like acceleration, which you might want to bring on an elevator, support remote logging. All right, I see the question from Judy there. Yeah, so the memory, the data is stored on the sensor even when it loses power. So it's not cleared. You then, if you found it, if I went out 24 hours later and hey, my CO2 sensor battery went out, all the data I'd collected for that 18 hours while the battery was good is on the sensor. I would simply connect it to the computer to charge it up, and I could retrieve that data that is saved to the memory. Good question. All right, so those are all my activities. We've reached the end of our formal time here. I just want to mention a couple of things here in summary. We've looked at 3 sampling modes: periodic mode, which is great for live viewing in SPARKvue at a periodic sample rate, or it's what happens on a logged sensor, as we saw with wireless CO2. Manual mode is great when you want to associate data from a sensor with user-entered data, whether it's categorical, like names, or numerical. And scope mode is great for fast-changing measurements like we saw with the sound level and some circuit experiments. We've also looked at some new displays, perhaps new to you, including bar graph, text box, assessments, and the scope and FFT displays that enable the scope mode for fast measurement. So I want to thank you so much for joining us today. If you have any more questions around the world, you can go to this URL, pasco.com/support, and get in touch with your local Pasco rep or Pasco technical support, and we'd be happy to answer any questions you have.